Machine learning is one of the most used technology in today's world. But why? Why it's getting the popularity the companies like Google, Ola, Uber are currently using. But there are lots of features we get when we start using machine learning. We can make our own model as well. And there are few types of machine learning we have, like supervised learning, unsupervised learning, and reinforcement learning. But we do have also algorithms under these categories. So keep that in our mind. We came up with a tutorial where we are going to talk about what is decision tree, how it comes under supervised learning as well, and what is supervised learning stands for, right? So before start the tutorial, let me introduce that Great Learning has came up with a brilliant idea, that is Great Learning Academy, where you will get almost 80 plus free courses, and after complete your course, you can claim your certificate as well. And if you want to do these courses in your mobile application, that is also possible using Great Learning app. So let's get started with the tutorial.
Decision trees are a very interesting set of techniques. I'll tell you why. Because this formed a fundamental step to what we're about to learn, or what we use. So we took decision trees and built a lot of them together. It started becoming what we call ensemble learning, the French word for meaning. Right? But in terms of decision trees, the key attribute here is it is a kind of a binary or a multi-split tree that will start with one root objective, try and help you build a classification or a regression. Regression again with target variables and having a least standard deviation. We'll try to branch out where the standard deviation is the lowest, and in classification you try to use an indexing method. Right? So what is this indexing method? We have something called as a measure of impurity, which happens to be the Gini or entropy. I'll talk about that. Right? The whole idea is it is a branching tree that will help you reach the highest form of homogeneity with your target kept in mind. A very simple essence, the decision trees help you reach the highest form of homogeneity, so that bearing the target in mind, right? So it is used for classification most often and regression very rarely. It can be used for binary classification problems. It can be used for multi-class classification problems and whatnot. It's a very interesting thing. What it tries to do is it will try to find a relationship between the target and the independent, and tries to give you a branching structure that will help you achieve this classification. So what you want to do, it will start slowly branching out, and the branching stops only one of three conditions of met. A, there is no more information gain possible. Information gain, by that I mean no more Gini gain possible or no more entropy possible. Or B, the max sample, the min sample leaf is not met, or the min sample split is not met. Okay? We will talk about these points, the min sample leaf and min sample split. Was that point of min sample leaf, min sample split discussed on the videos?
Shyam, can you repeat your question? I did not catch your last.
Was the concept of min sample leaf and min sample split?
It was there in the assessment. I couldn't find it in the videos.
Okay. So min sample leaf and min sample split were not, not discussed in detail, or just given a basic idea, right?
Yeah.
Right. You also you have seen one control parameter called as max step, correct?
Yeah, max steps, yes.
Yeah. So the max step is a more crude way of pruning. Min sample, MSS and MSL are much more better variants of it. I'll discuss one. So the idea is the tree keeps growing until either one of these three conditions, or the entropy or the information gain is further not possible. So it tries to understand and gives you a splitting criterion that's run on top of all your variables at every level of the tree. That will help you achieve the highest form of purity or highest form of homogeneity in the target classification. Right? So that's the core objective of decision tree. Now, if I want to give you the variants of decision tree, there are a couple of them. What you would have seen would have been called as CART, or classification and regression trees for short. You have another type called as CHAID, which stands for chi-square automatic interaction detection. Right? Automatic interaction detection. right? You have something called as ID3, which stands for information dichotomizer 3. So these are all different variants of decision trees. Decision tree is a broad classification regression algorithms. Shade is more specifically used only for regression classification, and shade is almost out, which means that it's not in use at all. Very rarely do we use shade, right? Because it assumes all variables to be categorical. If it's not, you'll have to convert them. Only then will it be able to process. Card is a little more easy. Classification is a little more easy. It accepts both in numeric as well as categorical, right? Now, this is just a general perspective or ideas into classifying or doing this regression. So what I'm trying to do here is what I'm trying to say is I have two variables called x1 and x2. I'm building a scatter plot on top of them. I have reds, I have blues. What I want to do right now is draw these boundaries or find out this measurement boundaries that will help me classify that will give me the highest form of purity or highest form of homogeneity, if you will. That kind of, lets me classify the reds and the blues with the proper splitting criterion in place. Right. Now, the key point I would like you to note or notice here is the variable x1, x2 are tried at all levels. Which means that after the first split, it's not the fact that I'm going to overlook x2. I'm still going to try and see if I have to find a value in x2 that will help me do stuff better. If I have multiple other points scattered inside, I want to kind of do that better. Right? So in that context, all variables are tried at all levels of split. Maybe if I have a split value earlier, I'm not going to try the same value. I'm going to try something lower or higher, depending on what is going to give me the ideal situation. Right. So if I talk about a variable split, right? So what happens is I'm essentially saying that I'm going to try multiple, I'm going to try the same variable or same variable. Say initially, if I look at it, I split with x2, right? And when I'm splitting with x2, when I reach the next level of split, so basically I'm branching out here, right? So even if I reach this level, I'm going to try and see if I can find any more information gained or any more information enhancement with x2 being tried again. So that is what we call as the multiple variable, all the variables tried at all levels of split. May not be the same value, maybe a different value, right? So this is an objective or this kind of an information sense of decision trees approach or modulus operandi. So any questions? Is this part clear for everyone? Anything on previous sense that you guys need a little bit of clarifications with, or you need some pointers with splitting?
So Sam, in this case, how we can decide the root? Just like, for example, in this example, you are saying that the value of x1 greater than 0.6. How we can decide the root? From that, we can branch the two.
So the root is the entire data itself, sir.
Okay.
Root is the entire data sample. The first split criterion or any split criterion is basically chosen based on the parameter I choose. For example, it is either chosen based on Gini or entropy. And based on these two criterion, I will decide what is the value and what is the variable I want to choose first. And in that variable, what is the value I want to choose to export the highest purity or high. That is what I want to ideally measure, right?
Right.
Right. So we will talk about the error computations and talk about all of that. So Rajiv, pick point. If you can tell me which error, because the page 12 of the PDF, are you talking about the one attached to the LMS?
Yeah.
Okay. So I'll walk you through the process. I'll walk you through how this is computed. So if you have questions on top of that, I can, once that's done, if you can tell me if I missed out that error computation, I'll also be happy to reiterate.
Sure. Okay.
Right. Two measures that we have as impurity indexes, right? So one we have what we call as entropy, which is the measure of uncertainty, right? And the other what we call as Gini. Now, very simple. If I want to explain this, if I want to explain Gini in a very easy and simple understanding, right? we usually compute Gini as how a randomly chosen element from a set would be incorrectly labeled. So the objective of Gini is to see how a randomly chosen element is going to yield a level of incorrect label. So basically that's the impurity scale, right? So if we talk about impurity, we say, okay, the measure of Gini will tell me how impure or how pure the variable is likely to be. Entropy is a similar thing. Now between Gini and entropy, another major difference is if we talk about Gini creating variables as categorical, which means that I'll have exact measurements or exact values. Even if I have numerical, I'm going to be talking about values of less than or equal to, or values of greater than or equal to, or values equal to, right? And whereas with entropy, we treat values to be continuous values. So we basically take their logarithmic coefficient and say, okay, how much of this essentially existed and how much did not. So very simple, very, very, very easily, intuitively understanding. So the idea between Gini and entropy is, if I choose this variable and this value, what is the likelihood of me encountering an impurity scale versus the purity scale? So both 0 indicates highest purity. Gini maxes out at 0.5. Entropy maxes out at 1. So 1 indicates absolutely nothing to do with purity or nothing useful with that variable and that value. 0 indicates highest form of purity, which means that no further split this aspect. Rajiv, if you want to quickly check, are you talking about the computation of Gini and the errors? Or is it a general scale of how the error is computed with say the Gini or
Maybe let's first go to the general scale, then we'll come to Gini. Gini, I've got the concept.
Mm-hmm.
Yeah.
Right. So when we say error, right, we usually measure okay. So when we talk about error, are you talking about the error in a node versus 0 to 1? Is that the error you're talking about?
Yeah.
Loss? So there's something called as loss or error that we compute at a branch, right? Is that what you're saying?
Yes, correct. Yeah.
Okay, perfect. Right. So I'll talk about it. So I'll walk you through that. There's also some other parameters I'll talk you. So general, how you compute Gini. So Gini is the most commonly used. Right? So this is a formula. Don't worry about the formulation parts. Intuitively, what I'm going to try and tell you is, I'm going to say, okay, which variable at what level is going to pass. So generally, we first compute the Gini index, right? So Gini index is computed. When I say Gini index, I usually calculate 1 minus P of j given T, summation of j. Right? So for all classes, the whole square. And Gini gain is computed as, right? So Ni by N, where Ni is the number of variables of that particular class, divided by the N is the total number of variables, into the Gini of that particular variable, right? This is how you compute Gini gain versus Gini index. So Gini index is basically telling you what is the level of purity that value in that variable can give you, or how impure or pure it can give you. 0.5 indicates that variable is useless. 0 indicates it's amazing. The lower the Gini, the higher the information gain I have. Right? Similar case with entropy. Entropy is minus summation of P of j into log of P of j. Right? Don't worry about the mathematical formulations. Absolutely nothing to do with that. Let's probably throw that out the window for now. Right? The idea is, all I'm trying to do is get the sense of what variable is working well and what variable is not working well, and what value that variable, if I use for splitting, will work well. Right? If I want to break it into a very, very simple sense, I just want to talk about it. Right? The tree grows. The tree usually has a tendency to overfit. Decision trees have this tendency to overfit, which means that they get too much into the training data, and if you don't control this, it usually gets too deep into the data. Right? By default, if I don't give any parameters, the MSL and the MSS is usually 1 and 2. Right? So the good guideline to avoid overfitting is max depth is 1. Right? That is a pruning method. So max depth is 1. But what happens with max depth is, I want to know where to prune, or which is the ideal option of how to prune about it. This does not essentially solve that problem for me. Now, what ideally works is we usually set this parameter called min sample leaf and min sample split. So, have you heard of these terms? Was there any explanation about this?
No, not in the videos. No.
Okay. So, min sample leaf is a very simple parameter. Right? So, if I'm designing the split, right? I keep splitting. Now, what this min sample leaf will do is it will split or it will do a branching from what we call as a terminal node to a leaf node or to further down, further branching down. Only if I'm able to put at least these many number of observations in the last bracket. Is that making sense? Right? If I set it to 10, at least 10 observations should go on either. Minimum, there should be at least 10 observations on either side. There can be more, one can have more. So the other can have 100, 50, whatever may be the case. But the other one should at least have 10 observations.
Can you repeat that, please?
Okay. So let's say I have 50 basic data points I have, right? And I'm splitting 30 and I'm splitting 20 here, right? From this 20, or if I want to branch down further, if I want to split further, or the condition, if I want to call something as a leaf node or a terminal node. Now, a terminal node meaning there can be more splits. Leaf node means that it's just stopping there. Right? That's the last node in the tree. Right? Now, if I want to split further, one of the conditions that I have to check is this. I can set to check is this min sample leaf, which means that if I set min sample leaf for 10 in this case, this particular node will only be split further if my splitting criterion, right? So basically what am I doing? When I say split, I have a splitting criterion, correct? You're able to follow me? There is a splitting criterion attached here. With me so far?
Yeah.
Right. So when I say splitting criterion, it's saying that let's say x2 greater than 10, which means that it will go look in this data and look from this particular subsetted data, it will look for x2 greater than 10 and it will finish and put them in these observations here, correct? That is objective of splitting criteria. Right. Find a condition and then, the observations that meet this condition, put them on the left, observation that won't, put them on the right. You agree with me on that?
Right. Yes.
Now, in that sense, if I say min sample leaf is 10, if a splitting criterion is not able to produce, if any of the splitting criterions are not able to produce this part where I'm at least having 10 observations in each of these buckets, minimum should be 10. There can be more, right? Minimum should be 10. I will essentially not split further. I will make this to be my leaf node. You able to follow my point?
Yes. Yeah.
Right. Is that making sense for the others as well?
So basically, you're saying it doesn't make sense to split anymore because it doesn't give any.
Correct. It doesn't meet this consideration. Yes. So what happens is, so this is something I control. I will say this min sample leaf is at least 1% of my data, which means that if I have 10,000 records, I'm saying this particular branch or rule that I have should at least have 100 records for me to even make sense out of that rule. That's fair enough, right? If I have totally about 10,000 records, I'm saying 100,000 records, right? Or a lack of records, I'm saying at least 100 records should exist in that bracket, or 1,000 records should exist in this bucket. I want at least 1,000 people. Let's say my objective is a targeted marketing campaign or targeted email campaign. I'll tell you the use case of decision trees also, but since we brought this topic up. So let's say my objective is an email campaign, right? And my past histories and successes have given me some information. Now with decision trees, what I will get is a set of comprehensive, interesting rules that will give me the leaf node, and the leaf nodes will also contain a success percentage of people being in that bucket versus failure percentage, right? For example, if I have a rule that says age greater than 30, right, and salary greater than say 1 lakh a month, right, and all these conditions are met, my success of this email campaign is 80%, correct? Now, if I want to use this 80% to my advantage, I want to have at least 1,000 people from my total data set. Only then can I target these set of 1,000 people for my next marketing campaign and make a better success rate than the initial start point. Does that make sense?
Yeah.
So a major pro of this decision tree is it gives you like a gray box. So, some of these algorithms are black boxes, which means that I don't know what's happening inside, but I know the mechanics, but I don't know what variable is causing what level of results. With this, I can understand, okay, so these are the variables with these levels that will give me an 80% success rate. Especially a 20% failure rate. I'm okay with that because my initial start would have been 10% success rate and 90% failure rate. Right? I can probably come down to this particular point right about here. So that's the big advantage of this. So a big use case with this decision trees is it's used in a lot of marketing campaigns. So there's a problem we're solving for Adobe. When I was working with LatenView, where there were email campaigns being targeted and we wanted to know who the perfect end customer would be. Right? So we built a data set, we built the different use cases of products of Photoshop and all these things. And we said, okay, what are the tools they're using? All these information gathered. We said we'll build a decision tree. And we were able to build a decision tree and make a very, very tangible result for the customers to start using. Okay? That's an interesting use case for decision trees. And there's also another problem we solved. Right? So this problem again was for this product that we call as Smart Insights, where we built a decision tree to get me the rules that I wanted to follow. For example, I don't want to build a black box where I said the customer can give me the list of ingredients. I can tell them what works, but rather I was interested in the social media problem where I wanted to give them what should they focus on to get a better success rate in the historical product success rate. Did we ever talk about the data preparation for the stochastic problem, for the Smart Insights problem, for the social media problem?
No.
Does it strike a bell with anyone? Okay. So let me give you a quick walkthrough. Okay. Before I do that, min sample split, right? So is the condition where is a prima facie. Right? So where I'll just explain this. I'll give you the use case. So when we talked about min sample leaf, is that clear for everyone? Any questions? All right. So min sample split is another interesting thing where should I split this node for any further? If I say min sample split is 30, this node will never be split because it's simple. There's no 30 observations at all in that branch for me to split any further. So that becomes my leaf node. Right? Very simple. Min sample leaf is how many should I be able to split or give brackets to my children? Min sample split is the parent node. How many should there be for me to consider it to be split any further? Right? The usual ratio between min sample leaf and min sample split is 1:3. A min sample leaf is usually 1%, at least a percent of the data if it's a big data set, or higher to up to 10% or 15% for a smaller data set. Okay? So these are the two things that we have with min sample leaf and min sample. Any questions?
Shyam, till now, all the trees that we have seen has only splitting by 2. Is that a rule, or can we split by 3 or 4?
Yeah. For decision trees, especially cart, it's only a binary split tree. So it's a fixed binary split criterion, whether the criteria is met or not met.
Okay.
I remember I talked about Shade. So Shade is a multi-split tree. It can split more than 2. It can split up to 3, 4, more than 4 or more. But cart is a pure binary split tree, which means that it can only split yes or no. Condition met or condition not met.
Okay.
And we use these MSL or MSS in conjunction, or usually, or just we only.
It's an explicit parameter we start specifying. Right. So if I don't do that, I might end up with an overfit tree, because by default MSL and MSS is split to 1 and 3, 1 and 2. Max depth is set as 0. I mean, max depth is set to infinity, but just don't control the tree at all. We use max depth to control, but as I said, it's a crude way. It won't essentially measure or take any account or relativity to the target or to the data set's populace, but rather just arbitrarily specifying where do I want to stop growing the tree. Right? We may end up with an overfit tree, or we may end up with an underfit tree also. We might end up with losing more information. Generally, MSL and MSS, from my experience, has done a lot more good than going the other way around. That's the option, sir.
So basically, you either use an MSL or an MSS. You
Both together. We usually specify both together, sir.
Both together. Okay.
So we specify min sample leaf first, and then say that's 1% of data, maybe in this case, 100,000 records, 100 or 1,000, and min sample split is 3,000. And it's usually 1:3 ratio.
Okay.
Not a rule of thumb, but a more generic advice. And any questions, anyone else?
And these in turn takes care of that reduction in the error rate and all, because basically you do branching, only if you get some value, right? I mean, that's what I'm keep on saying, same thing. But he talks about some threshold. I mean, about like if you go from one branch to another, in the reduction, the error, if it is greater than a particular threshold, then that makes sense to branch. Otherwise, not.
Right. So the error criterion or the weight criterion, I think that's something. If you can just point me to that exact link, sir, I can help you debunk it.
Okay.
I'm not. So if you can just share that source with me, I'll probably look at it and clarify as comments or any comment that I can.
Okay, sure. Yeah, I will post it in that. It's in one of those videos.
I just like to. The reason is I'm not able to get a clear 100% context of the error threshold that you're talking out here, right? So I want to be sure before I answer that question.
Yeah, sure, yeah. Because it is not there in the hands-on session. And the hands-on, I think we are only using a max depth, and there is no error criterion. But in the videos, he was specifically mentioning about that error.
Let me clarify. Okay, so let me just clarify this. I think in the videos, you would have seen something to do with an implementation on R, where we talk about pruning the tree. The pruning tree comes with the cost complexity or CP parameter. Right. So the CP is used as the error control parameter that says CP of this is giving me the lowest error. So it means that I'm going to use that, not a zero. Is that what you're talking about?
Yeah, that's correct. Yeah.
Okay. The cost complexity parameter is specifically used, or a CP is used in a pruning method or alpha parameter that we use in R. So R has a package that helps us understand or control this depth. In Python, we use a max depth or min sample leaf and min sample split. So Python does not provision or give you a provision to use this CP parameter.
Oh, okay.
Right. So the cost complexity or CP is like I showed earlier, right? So the table is you will have CP, you will have N split, you will have relative error, you will have cross error, you will have standard error. Right. So CP will start with a 0.03 and N split will be 2. Relative error might be around 0.8 or 0.95. Right. 0.02, 0.2, N split is 4 or 6. But I mean, N split can only be 4. Right. N split is the number of splits or number of leaf nodes you have here. That's called the N split. Okay. N split is this plus the terminal nodes that you have. So you have the relative error going up. Going from 9.5, it will go down to 9.2. All these. So this CP, you will decide at one parameter where the relative error is lowest, and after that it starts growing. So this threshold is what you'll be using to prune the tree. Right. So you'll be using something called as pruning to specify the tree that you built. You specify the parameter and you specify the value of the parameter.
Okay.
This is what you'll be using for the pruning step. If I understand your question right, I think this is the one that we are talking about. Are you talking about the same thing, sir?
Yeah, I guess so. I mean, I probably may be wrong, but basically you have that formula, right? 1 minus sigma pi squared. So basically in the videos, he was talking about the root node had like 0.5, let's assume 0.5 as the value, 1 minus sigma pi squared.
Yeah. So,
branches.
Okay. So this is the one that you're talking about, right? 1 minus summation of I. So let me just clear this out. So I think you're talking about 1 minus pi summation of I whole square, correct?
Right.
So you compute where we say probability of zero, the male given the target, the whole square, plus probability of female given the target, the whole square. Right? In a banking data, if I want to talk about a marketing campaign or any marketing campaign. So you compute this thing that if it is 0.5, you say 0.5 omit.
Right.
You say don't do this because this is highest form of impurity. Correct?
Yeah. Yeah.
So this threshold, or we want this to be the lowest possible. This error that you're seeing here, this is used for a split criterion or decision to choose a split between a variable.
Right. Yeah.
Right.
Right.
So again, if you can still point me to the point, exact location, I'd be more than happy to clarify even further on top of it.
Yeah. Right. Yeah. I mean, so if a root node has, let's say, 0.5 and the subsequent, like the next branches as if it is at least, it should at least be less than that, like 0.4 or 0.3.
Yeah. Okay.
So then only you should basically branch, and you should not branch just like that. I mean, if it is 0.5 and if the value is like 0.495, the root branch, I mean, there's no point in branching. So that is what the concept we are talking about.
Okay. Okay. So you're saying at 0.5 and 0.4. So basically, this is a Gini gain or entropy split gain.
Yeah.
As you keep going down the node, there is only so much of information gain that you can achieve, or so much of purity you can achieve with a split. Which is the max depth is what we use as a control parameter. Right? So max depth is I want to stop at this level of purity. I don't want to go beyond this level of purity. Right? So that's a computationally specified parameter there.
Okay. So max depth controls that impurity.
Yeah.
Okay.
Basically, how much of overfit are you doing or how much of underfit are you doing? That control is that is done by the control of max depth.
Okay. Thank you.
So this one particular problem, I don't recollect if I've discussed this with everyone, but okay. So the data was, the problem statement was we had a client who had about 5 different things, who had 5 ingredients, who they wanted to know, will it become a mainstream, which is consumed by mass public, or not a mainstream, right? Or will it fall dud, or will it fall between 5 categories? So basically we had mainstream, trendsetter, early adopters, influencers, and followers, right? So this is a kind of 5 different brackets we had. So our objective was only to predict mainstream. So the the customer wanted to have any ingredient classified into this. So how did we do it? So we had the data broken down into a stochastic scale, which is I had my earlier data set had data from 2015, the first month, right, till 2019. I think I was doing it 18, right? So 18 till the 12th month, right? So this is for one. My data set had for, let's say, I'm using for avocado. This is for skincare. Right? So so my ingredient I had information for this. So what information did I have? I had information on the number of tweets, right? Social media information. I had number of tweets. I had number of YouTube videos. I had number of blog articles. I had number of forum discussions. I had number of news articles about this ingredient in the skincare spectrum. I had number of YouTube comments. Each of these videos had YouTube comments. You had different information, right? So tweets is the biggest source. We had likes. So within tweets, you had the likes, number of likes. You had number of shares. All this information. So this is my social media information, right? Then we also had e-commerce information, where how many products did I have in Amazon, how many products in Target, how many products in different stores. Okay, so you had Sephora, all these Ulta Beauty, all these stores. You had number of reviews, number of let's say products in cream form, number of products in say oil form, all of this. So this is a data set we had, and the target was whether the product was mainstream 1 or 0, right? Number of YouTube influencers, all of these people, all this information. So that's the information I had for this, and this was available stochastically. So I had the delta, I had the cumulative, as well as I had the absolute numbers for that month as well, right? Now the objective was to build a mainstream, yes or no. It wasn't enough for the clients just to build a nice objective of yes or no, but what we also gave them is rules, where we said if you want to have a 90% success rate of your item going into mainstream, you should have influencers beyond these numbers. So you have a number of videos in YouTube beyond these numbers. So what happened was this was achievable. This particular information was possible only because we were using a decision tree. Right? It gave us nice, beautiful set of rules that had a complex set of information that said, okay, look, have this data, have this format, follow this, and this should give you a indication of whether an ingredient will become successful if you follow this, versus a failure if you don't follow this. Right? So this is a very interesting use case that we use decision trees to solve. Is it understandable by the others? Is it understandable by everyone? Is the problem statement and the data preparation, is that sensible? Is that understandable?
I mean, I probably lost focus in between, but I think is this because you're trying to do is like to with these ingredients, whether it would work or not to market in the market. I mean, whether it would be successful
right.
product.
So, what happened was we had around 120 ingredients where we had this data set. Right. So for 120 ingredients, I had data from 2015 one, where each of the social parameter was there. Each of this e-commerce parameter was there. I also built additional text analysis parameters like variables like functional, emotional, and technical drivers, multiple other things. Right. So I had 110 ingredients, each of them having at some point whether did they become mainstream, yes or no. Within the span of 3 years, right, from 2015 to 2018, amongst these 4 years, did this ingredient go from 0 to 1? Right? So whether it was ingredient in the mainstream, or was it a mainstream to start off with, was it a mainstream in between, all of this information we had gathered, right, with the data prepared this way. Okay. Now, when we had the data for these 5 ingredients, we collected data for these 5 ingredients. I'm not at the liberty to say what these 5 ingredients were, but we collected data for 5 ingredients. Let's assume for now they're orange, apple, and all these things, right? For skincare. We collected data in this very similar fashion for these 5 ingredients. Now, what we had to predict was at every month or at which month will this particular ingredient go into mainstream. So that is a prediction problem we had. But we also went a step ahead and said, if you want to make your ingredient go into mainstream, with the current data or the current live environment, with the current information that we have, your ingredient will go into mainstream at this date, will not go into mainstream at this date. All this we predicted. That is something the prediction we made. But we also said, if you want to make your ingredient go into mainstream, these are the rules that you have to follow, that we computed by our decision tree algorithm, that overlooked this information, that collected information, the history, and said, look, there's an 80% success rate if you have more than 500 YouTube viewers, or if you have 100 blogs talking about it, more than 100 blogs talking about your article. And if your product is in the form of oil, in say more than 10, number of products in oil should be more than 10. If you are able to do that, you're looking at an 80% success rate. So that is a very clear indication of how a company would like to operate. Right. So in terms of a manufacturer, you want to have this information to say how do you want to tap the market or approach the market. Right. Okay. So now what we're going to do is, this data set is a classic data set. We're going to have this problem statement, and this is wine quality prediction. So we have about 6 targets of wine quality. We have different information. We have parameters of the wine and all these things. This is the attribute information. So I have red wine is 1,599, white wine is 4,899. I think to all of you that we're solving the last problem, you would have found most of your algorithms not doing it justice. Is that something that you felt? Is it something you saw as well?
I still haven't finished it, so I am listening.
I think the reason is, if you look at the target event ratio, you will find the target event ratio to be 91% and 9%. That's a pretty imbalanced data if you ask me. Right? And invariably, all algorithms that we've seen so far, the pre-processing, will suffer terribly at that scale and spectrum. Right? I think I would definitely think believe that it was the case there. So this is a data set. We're talking about what is the data set we have. So we have fixed acidity, volatile acidity, citric acid, residual sugar chloride, all these things. You will have this, the description of the attributes. General point of advice when you're when you're data scientist, when you're working with all of these, please be inquisitive to try and look at information, right? Try and look at understanding all of these, and then make your implementation or model predictions or whatever, right? Yeah, but the imbalance, did anyone else find the imbalance to be kind of off-putting? As in your models were not doing any job at all.
We are talking about which one, project or project?
Yep, project. The data set you would have seen would have had an imbalance, right? I think I saw the ratio. It is 91% to 9%.
Oh, you mean to say people who took loans was 9%? Yes, yeah, that was there.
Yeah.
So Shyam, what you're saying is like when you have those. Okay, so sorry, please go ahead.
Please go ahead.
Yeah, so when you have that much imbalance, mostly your models would not give you an accurate prediction. Is that what you're saying? I mean, generally,
your accuracy would be through the roof. Let me be honest. Your accuracy would be 95, 98, 99, right? That's almost too good to be true. But look at the precision. But look at the precision and recall score, and right. So you look at the precision and recall scores of class wise, you will find that it is in stark contrast. You will find the 99% attributing mostly because of your zeros. The class of ones, you will find them very rarely confirming up to the accuracy numbers. You find the precision is almost impossible to be, it's almost unusable. 99% is not justified. So that's a pretty common problem we face what we call as class imbalance. There are ways we handle that. You will learn about it shortly, but just to give you a peek, it's called as, there is a technique that we call as oversampling or undersampling technique. The undersampling is to undersample the majority, oversample is overpopulate the minority. Then there's a technique called as SMOTE, which is synthetic minority oversampling technique, which will oversample the minority and undersample the majority. So you will understand about all of this. Unless and until you do that, your training model is absolutely going to go bonkers. You will find no tangible results usable. Right. So here
so
we
how is
have
that related to this that you're saying?
No, just giving you a perspective, sir, because the target measurement is always important. So I wanted to reiterate that. And this is not related to this context, but I think when I was talking about the target distribution and all these things that we have discussed here, I wanted to add a point there as well. So we have 1,600 records, 12 variables, and these are the parameters that we can use. So all of them seem to be under a conformed scale. There's not too much of explosion or extreme outliers in some context and sense, right? And as I said, as I requested earlier, if you're having a univariate analysis, having it on the lines of data understanding with statistical numbers are fine, but also look at it from a perspective of how it impacts the model and all of these information. I think that's a very important attribute to have if you ask me. Right? That's something that's always important as a developer or as somebody who's understanding a problem to solve. Now, if you notice, this is my data. So you have the quality at 3 and 8 seem to be almost negligent. 3, 4, and 8 seem to be negligent. So we can merge 3, 4 with 5 and 8 with correct. So that's something you can do just for the objective of this study. I'm giving you that, but in real world, we usually don't merge targets. We see if we can rewrite the rules for the targets, we usually do that. Otherwise, we keep them as they are. Right? In some cases, we usually merge them. There are different problems in which we merge them. Right? The fixed asset we seem to be almost a normal, not a perfect normal, but it's slightly right skew. Now, I just want to look at the correlation map to you, and let's see how we reach in the data there. Right? Now, look at this and tell me, is it something that you find interesting? The citric acid and pH levels are related, but not too much. Right? That's kind of odd if you ask me. Ideally, they should be, right? The more the citric acid, the more the pH should be. Right? And fixed acidity, like pH, as a good strong target. So this is a way to identify and understand relationship between variables. And as I mentioned earlier, not your pure benchmark or baseline. So please be very careful and very sure of that factor. All right. Any questions so far? So normalized 2 will give you ratios. If you don't use normalized 2, you will usually get the absolute forms. Right? Now, what we're going to do is, this is something that's common. We want to create a balanced variable. So there are cases where we use Pareto principle. If there are more than 10, 20 classes, we have this Pareto principle. Has any of you heard of this 80-20 rule?
Yeah. It's part of testing.
Correct. So the 80-20 is part of the testing, right? 80% of those. So here the Pareto principle, we do this root cause analysis or all these analysis where we look at 80% of the variables, or if I have a cumulative percentage of 80, I stop that as my threshold, and anything that's beyond that 80, I add it back to I add it as common group of others or things like that. So in a similar sense and scale, it's now going to combine a few groups, right? I'm going to combine 3 with, let's say, I'm going to replace 8 with 7. I'm going to replace 3 with 5. I'm going to replace 4 with 5. So like I said, this particular chart gave us the fact that there are two scattered information available. So I might just group them together. Right? So 3, 4 will always form into 5. 5 being a very normal measurement. So the inference has to be in coherence or in line with that particular contribution. Right? Okay. Now let's do the brain test split. Yeah. Okay, so I'm doing this. I'm just taking the target. I'm doing the target quality on this, and we have the data ready right about now. Okay, so let's build a very simple decision tree first. I'm going to go with the decision tree. I'm going to use the criterion to be Gini. Right, and let's create this. This is my map. Now, I want to pay key attention to this particular parameter. Remember, if I don't specify this, I told you, right, it will be 1 and 2. The tree is essentially likely to overfit right away. Okay, that's a very, very important attribute. If I don't use this control parameter, it will automatically go into unlimited. So the max depth is by default none. You will end up with an overfit tree if you don't specify or have an explicit specification of my target. Okay. Now let's look at the decision and then review this. Let's look at the target and then review what I mean by that. Right. Sorry, this is the model Gini. What a wonderful score. I have 100% sanity. But will it stay hold true if I go for the, Currently not. Right. So remember why we said the overfitting is important and you're not supposed to, overfit it or control all of this. And let's see if we can change or do something about it. Right. Let's say I'm right now going to, instead of max depth, I'm going to change this. Let's say I don't want to use max depth. I have 1,200 records, right? So that's 12. And 36. There we go. Right now, let's probably get the measure of this. Only 3%. Not 60%. I think the model is still suffering. You need to have a few more iterations. So it's a good thing. You building a model and trying a lot of these things is a good thing. Right now, it's not at least a complete overfit. It's just a partial hope or there's a different thing. So that's why we need to build a lot of these into accurate. All right. Now, very important, very aspectual thing about this is you can use this method, you can use this tree to calculate what we call as feature importance. So which feature was the highest in terms of importance and which feature did we use well, what gave us the best accuracy is something that we can look to solve or get the understanding. All right. Am I making sense here?
Yeah. Yes, sir.
So this is the feature importance that we are getting here. These features have turned out to be the most important. Alcohol content happens to be the most important for quality, followed by sulfates, followed by total sulfur dioxide. The pH level, like we said, with citric acid, acidity, all these things are taking the least priority. Right? In terms of the highest priority, the feature has the highest for your alcohol content in the tea. So this is a way of looking what feature turned out to be the most important, what feature is the best option possible, and so on.
So this feature is like in your previous example. If we are looking at writing block, we should be writing about alcohol in the product more like that.
So yeah, with the context, the presence or the context of alcohol seems to be the most important for this particular decision tree with the data sample that we have given. Right? So in that sense, it's been, so what I say that the decision tree used alcohol content to be the splitting criterion more than anything else, which means that was the most important feature that was used to determine the best split. And this feature is computed against how the purity of that variable will change when it is not when it has different values and how it effectively works in the decision tree. That is what we see here in the feature importance parameter. Again, this is in sense to this algorithm and to this data sample. Yes, your point can be right, can be scaled up, but for that we need to have the rules. I will share the script with you. So there is one package that I cannot install in my local machine that is barring me from visualizing this decision tree for all of you. So I'll share the script with you that you can use to visualize this decision tree, look at how beautiful or how interactive these rules are. So unfortunately, my local machine does not allow me to install that package because of a version conflict. There's something else I'm working on, because of which I'm not able to roll back the version. But yes, you can try it. Have a look at it and have a go with it.
And by looking at this feature importance, I mean, the more the alcohol content, you can presume that in the quality would be high, right?
Yes. So in a slightly retrospective sense, the alcohol content helps me distinguish between 3, 4, and 5. The quality of 3, quality of 4, and quality of 5, right? So remember, we had our data set was prepared to have this quality.
Right.
So not necessarily that, but the alcohol quality or alcohol content in that particular wine helps me distinguish between 3, 4, and 5.
Okay.
Not necessarily the higher the alcohol, the better the wine is. So it doesn't translate to a linear correspondence there.
Okay.
So the more content the alcohol is the distinguisher or is the separator between quality 3, quality 4, and quality 5. So it's more towards the associated to the target. The feature importance is computed and associated to the target more specifically.
Associated target?
The target is the quality of wine, 3, 4, and 5. So if you remember,
Yeah.
we had this.
You said feature importance is associated with what?
The target.
No, target. Okay.
Right. So the more the alcohol, the more I'm able to distinguish between 3, 4, and 5. So quality 3, quality
Okay.
4, and quality 5.
Okay.
Not necessarily always corresponds to the fact that higher the alcohol content, the better the quality is. Right? So
Okay.
it's not a linear translation like that of the perspective.
Okay. Just have one more question. So when you after pruning, we got that score rates to 70 and 60, right? Whatever.
Right.
What would you usually do, like to see, like if you can increase the score and to better the model? I mean, generally you try to change that MLS or MSS.
Yeah, the ML and MHS. Yes, we do that. But doing that manually will take a lot of time and effort. So there is an automated process that we call as grid search.
Okay.
So what we do in grid search is we let multiple of these combinations of parameters be fed in. So I'll start with 1%, 2%, 3%, 4%, and then corresponding increases of multiple variations of these numbers. Right. And what I will try and do is see how these different numbers come up, and what parameter or what combination of hyperparameters gives me the best result out of the entire group.
Okay.
Right. So I iterate over multiple combinations, see which is the best possible option.
Okay.
So that's what we call as a hyperparameter search. So what we're looking at, the parameters of the model is what are hyperparameters. We iterate, we check over these multiple hyperparameters. That approach is called as a grid search.
Okay. So basically you can choose any of these, like for say 15 or 16 different parameters in that grid search. Which will try with different combinations of these 15, 16 parameters. And
which will, when we pass the parameter, we usually tries all these combinations. So it starts with one parameter, tries variating the others, keeps the next one, tries variating the others, and it tries all the n cross n combinations.
Okay.
So you have three in ML, 3 in min sample leads and 3 in min sample split. And you also try variating this, right? So it will try a 3 cross 3, a 9 grid of combinations. Right?
Okay.
So it's usually an NC3, permutation combinations. So it's 3 factor into 2 factor into 1 factor. Those many combinations you can try.
Okay. And can you just please scroll down a bit?
Sure.
So in this case, that pH value, like it's 0.005.
Right.
The feature importance is not that great. I mean, do you usually treat this as a measure of to drop it?
Not particularly. I mean, just because the feature is completely unimportant, determined by the model itself, does not mean that it has no correlation to the statistical, to the target in some sense. And so, as I said, that's not the pure and only based measure. The feature importance is not pure and only based measure. For some of these measures, depending on the business context and importance, we can drop it. Right. So to answer your question in both ways, yes and no. Yes, I can drop it, and because it's completely insignificant to the current model. So for this model, we usually drop it.
Okay.
But we don't drop it from the original data as well, because there are multiple models we try before we come up conclusively saying that the algorithm or whatever we're going to use, this is the final algorithm and this is the data set for that final algorithm.
Okay. Now, why I asked that question was like, basically when you have too many labels also, it makes your model more complex and it could be, right? So you have to take a decision whether to drop or not, or to dimensionally reduce it or not. So those kind of...
This is one option we can use it for.
Okay.
But when you're going to drop it, we have to ensure that we've tried across some multiple samples and a k-fold approach before we say conclusively that this variable does not have any importance at all.
Okay.
Right? Because sometimes what happens is in a single split, we might not be able to make a conclusive decision, a comprehensive decision that this data with this particular result is following the exact distribution of the population so that I can take a decision directly with one sample. We usually don't go for a single sample decision saying that, okay, this is that. So we do a multiple split, we do a k-fold validation, and then we say, okay, across all of these folds, this variable had the least ranking importance, so we can drop it.
Okay.
So that's something we can check as well. But yes, you're right. We do drop variables based on that. We compute, we do drop them, and we say it's not of any help or doesn't work.
Okay.
All right. So if there are no other questions for today, thank you very much for joining in. I will catch up with you all of the next week. We will talk about another new set of topics. Until then, stay safe, stay home. Have a very good week ahead.
So in this tutorial, we have learned about what is machine learning and what is supervised learning, as well as what is decision tree. How can you implement decision tree in your first project as well? I hope you like the video and do let us know in the comment section what you feel about this tutorial as well. And before complete the tutorial, let me introduce that Great Learning has come up with a brilliant idea, that is Great Learning Academy, where you will get almost 80 plus free courses, and after complete your course, you can claim your certificate as well. And if you want to do these courses in a mobile application, that is also possible using Great Learning app. Thank you so much.